Okay. Hello, everyone. Welcome for this webinar about the InSight Space mission. My name is Jean-Luc Berenguer. I am science teacher in France. You can recognize my French accent. And I lead actually the education and outreach space mission InSight. And for this fantastic and amazing mission, I'm going to present you some aspects of this mission. So I will present the main objective. After how his mission is going on, because it's already 1 year that the mission is on Mars, on the planet Mars. Then what are the first results? It will be a world exclusivity for you today. And for finally, we will finish by what kind of resource for schools we can provide for you, or which kind of resource will be available for you at that moment. So to begin, let me show you the first image of the ground of Mars. It was the 26th of November, so 1 year before. The camera on the InSight lander took this image. It was the landing zone, and this mission started 6 months before from California. You are going to see a little animation movie about this journey between the Earth and the Moon. And it was a not so long journey in the space. It takes 6 months. And it's not so easy to land on Mars. And of course, because of the atmosphere is very tenuous, so there is not a lot of atmosphere. So there is a necessity to slow down the speed. And it's the reason why we need a parachute for the first time and then rocket. I think maybe we can load the movie. We will see. Let's go to see what happened. So you have the space probe. It was just the 26th of November. You can see the probe landing on Mars. So you are going to see the very big parachute. It's necessary to slow down the speed like this. But then we will need some rockets. You are going to see this. And the probe was arriving on the surface. So the parachute will be launched and some rockets will be activated to be sure that the landing was successful. And the landing was successful. It was the 26th of November, and we arrived in a very an area on Mars where there is not a lot of impact, crater impact. It was a plane that we call Elysium plane. Maybe we are going to see the end of the movie now. Okay, so why are we? Oh, yes. Why? The question is why this space mission for? In fact, we need to understand the. Okay, so we go to the next. Yeah. Okay. Sorry, but the movie is a little long. Okay. So the idea of this mission is to understand the formation and the evolution of the rocky planets. And so we need to know the interior structure of Mars. It's a question directly linked with the Earth because while the Earth is habitable, while Venus, for example, or Mars are not habitable. So as we cannot cut the planet in two pieces, we need some indirect data and information. And we will ask this information with seismology, precision tracking, and heat flow. If you look at our neighboring planets, like Venus or Mars, you see that they are very different. The atmosphere is not the same, the size is not the same, the color are not the same, okay. But in fact, they are very similar because if you look at the interior structure, and if you look at the interior structure, you see that all these rocky planets are a shared common structural framework. We can look at the iron-rich core, is a part of which is maybe melted. After you have another layer, a thick layer, a middle layer that we call the mantle, is rich in silicon, and finally you have a relatively very thin crust with less dense rocky material. All this layered structure come from the solar formation, the solar system formation. So that means 5 billion years. So 5 billion years, all the rocky planets had the same evolution. What we know is that the planet starts forming an accretion of meteoritic material, is the first step. Then, as the planet is becoming colder, the interior begins to heat up and melt, and then you have stuff happens. We don't know exactly what happens, but at the end, the planet has a crust, a mantle, and a core. But what is very important is the step number 3. Stuff happens, that means that we don't know exactly what happened during this period. And we think that InSight mission will give us some information about this crucial step. Why Mars? Because the Earth is very big if you compare with Mars. Mars is not so big, but it's not so small too. And if you compare with the Earth, Mars is relatively undisturbed. So that means that you can find the step of the history and the evolution of a rocky planet better than on the Earth, because on the Earth there is a lot of phenomenon who erase all the story of a planet. So we think that on Mars we have a good chance to have some information about the evolution of a planet. So the deep interior of Mars, that means that InSight mission will determine a lot of things, or wants to determine a lot of things. For example, the size of a core. And the core, we don't know if it's made with liquid or solid. We think that there is iron, but we have to determine this. We know also information about the crust and the thickness and the structure of this crust, and also the structure of the mantle. And finally, we want to know if the interior of Mars is, how warm is it, and how much heat is still flowing out. All this, they are the main objective of the InSight mission here in these things. So for that, all the engineer and the researcher of the NASA and the CNES in France, and the Institut Physique du Globe in Paris also prepare with other countries, a very nice lander that you can see on the slide. You can see a model here, you see, like this. And this lander has, of course, very big solar panel because you are very far from the sun, so you are not a lot of energy. And then on this lander, you will have a lot of sensors. I'm not sure to speak about all the sensors, but three of them are very important. One of them is what we call SAIS. That means seismic experiment for interior structure. It is a seismometer. This seismometer was made in France, and is very sensible seismometer. And this seismometer it is the first in the story of the space exploration. It is the first seismometer who is able to run on the planet. There is another sensor made by the German team that we call HP Cube. It's a heat flow and physical properties package. It is to determine the heat flow, but unfortunately, until now, this sensor is not working on the surface of Mars. And you have a third one sensor, very important, that we call RISE, Rotation and Interior Structure Experiment. And this sensor, the RISE sensor, is to identify the oscillation of the axis of the rotation of Mars. And this variation in the axis of the rotation are linked with the homogeneity of the planet. That means that we can learn information about the core of a planet using this kind of information. Of course, you have a lot of other sensors like environment sensor, pressure, temperature, wind sensor, and it's very important because it's environment parameter that we need to interpret correctly the data from the seismometer. In fact, you have directly on this slide the first geophysical observatory on Mars. It is the first time that we have this kind of observatory with a lot of sensors running at the same time and recording a lot of things about the atmosphere on Mars and what happens in the on the ground. And this observatory is something like to make some seismology on Mars, as we have done a long time ago on the Earth and on the Moon. On the Earth, the story of seismology began at the end of the 19th century. You can see here, it was the first, on this slide, you can see the first record. It is the first seismogram that we record about an earthquake in Japan with magnitude 5.8, and it was recorded in Potsdam in Germany. And you see, it was the first seismogram, so it was the first time that we have a record of seismometer. Then there is a lot of special discovery, like in 1897, we discover the P waves and the S waves, so these volume waves who are running into the planet. Then a little late, we find what we call the shadow zone. And if I go, we can see Morovičić. We find what we call the discontinuity of Morovičić is the limit between the crest and the mantle. And this discovery is only because you interpret the seismic waves. And at the final, we discover the discontinuity between the core and the mantle, and it was Lehmann. She discovered this in 1936. So seismology is a tool to interpret what happens inside the Earth, so the interior structure of a planet. And why it is possible to use the seismology? Because the waves, and especially the volumes waves, when an earthquake occurs, the energy is released, as you can see here, and then all the energy released in waves, and these waves propagate everywhere in the Earth. And if you have on the surface some sensor that we call seismometer, you can record the arrival of the waves after their propagation in the Earth. Of course, you have also surface wave that travel only on the surface of the Earth, and they can also give us some information about the structure. So if you can interpret what I call the language of the waves, you can determine what happens with the waves inside the Earth. And of course, we have to calculate a lot of things. So you have to interpret the record of the seismometer, what we call the seismogram. Of course, on the Earth, it was possible to determine a very precise model for the interior of the Earth, because on the Earth we have earthquakes, because we have plate boundaries, we have an active zone, and in this active zone we have a lot of earthquakes. Everybody knows the boundary in Chile or boundary in Japan, and all the earthquakes occur every day, big earthquakes, and so we have a lot of seismogram to record, because we have also a lot of seismic stations everywhere in the world. So we have a source, earthquake, and we have detectors, the seismometer. And with this, we can slowly determine the interior of the interior structure of the Earth. We determine that there is a core, we determine that we have a mantle, we have a crust, we have some thermal anomalies that we call tomography, seismic tomography. So we can do a lot of things because we have a lot of sensors, and we have also a planet where the earthquakes are very frequent. We have done this also on the moon. On the moon, we have done this during what we call the Apollo mission. The Apollo mission is now 1970, so Apollo mission installed 5 seismometers. So they have installed a network, not at the same time, because we have a lot of Apollo mission, Apollo 11, 12, 14, 15, 16, and all this mission install a seismometer. We install also some other sensors like heat flow, magnetometer, laser reflectors. But if we speak about the seismometer, we have a good network, or a sufficient network to record earthquakes. So on the moon, we record earthquakes, and all these earthquakes, so it was shallow moonquakes, deep moonquakes, yes, because we have to change the name of earthquakes to moonquakes, of course. And all these moonquakes give us a lot of I think I have maybe somebody has a trouble with the presentation. I don't know. It's okay.
Yes. You want to ask a question?
Yes.
Share the question.
Okay, so I continue. All the moonquakes give us a lot of data, and with this data, researchers succeed to build a model for the interior structure of the moon. With a core, we don't know exactly the size of this core, a mantle, and a thin crust, mainly made by basalt. So, in fact, we have already done this experiment of seismology to understand the interior structure of not a planet, but for the moon. For Mars, it's a little bit complicated because we have only one seismometer. So that means that we need some Marsquake. We don't know exactly if we can expect Marsquake. So it's one point that the mission will tell us things about this. And also, there is only one seismometer. So it's very challenging to try to know the interior structure of a planet only with one seismometer and maybe not a lot of seismic activity. So that means that the mission can help us to discover a lot of things that we have a lot of interrogation about this. So I'm going to go ahead and to give you more details about what happens with the mission. I need Eleni, I need the video. Yeah. So on this video, you can see what happens on Mars when it's a model. So that means that it's something that we expect, that is not something that we recorded until now. So in fact, if there is a Marsquake, you will have some surface wave who are going to go through the surface of a planet. You see this. Here, the surface wave will just arrive at the inside landing site, and you have the first arrival of the waves. Then, as Mars is not too big, we can expect that the surface wave succeed to make a complete round circle around the planet. So the waves arrive a second time at the landing, at the lander, and also at the third time, like this. Okay. So in fact, we will have, if the Marsquake is very big or big enough, we will have this kind of data. First, a seismogram with 3 arrival time. Of course, the surface wave begin smaller and smaller because there is some attenuation on the Mars, but Mars is not too big. And the attenuation is not too big too. So we think that we can get this kind of data. And why it is important? It was important because by the slide who arrived now, this one. If you have only one station, the station is there with the letter G, you see here. And the earthquake is the letter S, like this. So when there is an earthquake, you will have the first arrival time, T1, the second time, T2 and T3. But in fact, you don't know the distance between S and G because you don't know where is the Marsquake, because nobody is living there and nobody can tell you when the Marsquake occurred. So you don't know the distance, and if you don't know the distance, it's difficult. But in fact, with some mathematical parameter, and you can understand that the surface wave is going to go through the station like this one, what we call R1 is R is the name of a surface wave that we call Rayleigh waves. Then the Rayleigh waves is going to go making round a tour like this, you see, that we call R2. R2 is like this, the other side of Mars. So the station will record T1, Rayleigh 1, Rayleigh 2, and this third one is the same wave we are going to make one circle of Mars and more this distance. So if you use all this time, you can find the distance using this arrival time, of course, the size of a planet, and you can calculate the distance like this. So when we will have this kind of data, the InSci lander will know exactly at which distance the earthquake will occur. And it's very important because if we have this kind of distance, we will be able to calculate the speed of the waves. And so the speed of the waves is very important to know the structure of the crust. And step by step, we will have information about the surface, the structure, and of course, with the P waves and the S wave, we will have information about the interior of the planet. So it is because Mars is not too big. You have Mars just here, like this. It's not too big. And the attenuation is not too big too for the waves. So we can expect that waves can do more than one tour of a planet. And in fact, we will use this kind of mathematical equation to find information about the structure. We need more information, of course, but it can be more complicated. And so we will have surface wave, of course, but we will have also P waves, Nth wave, and these volume waves will tell us things about the interior of a planet. And all these things are important to, it's the reason why seismology can be useful. Of course, we have only one seismometer, but we need also source, and we don't know exactly for the source. Well, we expect things. We expect that by the satellite images, we see already faults on the surface of Mars. So faults means that we have morphology evidences of activity. So maybe these faults are active, and if they are still active, they can produce quakes. We expect seismic activity because Mars is not so cold, and maybe there are still activity on Mars. There is also old volcanoes also, and there is also excitation, atmospheric excitation. So the wind can also occur things. The wind, that means that when there is some wind, there is not a lot of strong wind, but they make some vibration of the ground, and this vibration on the ground produce movement of the ground, and so the seismometer can record vibration of the ground. So this wind, we know this wind, and we can expect some noise for this. We can come back to the slide, Eleni, please. It's okay for this one. We can also expect meteorite impact. Of course, satellite images tell us that every time we have a meteorite impact on Mars, like on the moon. So you can see here two images in the 4th of June, the 10th of June, and you see a crater impact. So that means if there is a lot of we have some crater impact, this crater impact will produce energy, and energy will release seismic waves, and these seismic waves can be recorded by the seismometer. Other sources is landslides. We know that we have landslides on Mars, and of course landslides produce waves. And we have also source about dust devils. So the seismometer is very, very sensible, and this seismometer, very, very sensible, is able to record these dust devils that we have on the surface. That means that dust devil has to go very close to the seismometer to be recorded. So we think that we have a lot of source, seismic source, and so the seismometer will be able to record waves, surface waves, volume waves, and will be able to know about the interior of a planet. Just now, a few slides to remember what happens in 1 year, because we are at the it's the birthday of a mission, because the mission arrived on Mars the 26th of November, so it's quite 1 year. So the mission began, of course, before to launch the rocket, because we have to build all the sensors, and some sensors are unique. It was the first time we produce and we create this seismometer. For example, the seismometer is very, very sensible, is very dedicated for a very big job on Mars. It takes time to do this. After we have the journey, it was a 6 month. I said this at the beginning. Landing on Mars the 26th of November, it was a successful landing. And as you know, maybe it's not so easy to land on Mars. And when the landing was done, the lander began by making a deployment of all the sensor, and the landing was in a very specific area, so you can see inside on this map. So that means that we choose a place where there is not a lot of crater impact. Of course, it must be not a big slope, very smooth and flat zone, so a very boring zone, in fact, on Mars, because there is nothing. But we need something smooth and flat, close to the equator also. It's very important. And it was successful because the InSight landed at the right place that people have planned. Then I showed you this first picture. It was the picture of the ground. It was the first picture of a lander with a lens cover on to protect. And this is another image of the ground. It was taken the sol number 4. Maybe you know that the Martian day is called a sol and not a day. So the sol 4, that means that it is 4 days after the landing. And you see that it is a flat and smooth area, but you can see a rock just in the middle of the image. That means that we're lucky. The lander was at a good position because the rock was not very far away from the place of the lander. And then we have also this kind of picture. So we have very, very nice picture. You are on Mars. You are on the lander. You see the robotic arm is this white robotic arm, and this is on the left the seismometer. Actually, at that moment, so sol number 4, it was on the lander, and then the robotic arm will deploy the seismometer. But before, he has to decide where to put the seismometer, so he has to scan all the place, and the decision was taken to where to place the seismometer and to the heat flow probe also. And this green zone that you can see on the image was the zone where we decided to place the seismometer and the HP cube probe. The soul after is to make it, so the deployment of the seismometer. You can see the seismometer on the ground of Mars. It takes time, of course, because to deploy sensor, you have to take a decision, you have to test, you have to check before, and you have to know, in fact, that before doing an action on Mars, every action must be tested. And what you can see on this slide is a slide in California, in Pasadena, on the NASA institution. You have a twin of the lander. It is the same lander because we built two landers. One lander is in Pasadena and the other one is on Mars. And before doing an action directly on Mars and making some order by computer, we test all the order directly on this lander, on the twin lander that is in Pasadena. So you can see that before making the order to deploy the seismometer and to HP cube, before doing that, this kind of action were be done directly on this in this area, and it's what you can see here on this slide. Now it's time for me to show you the first result. As I said at the beginning, is a world exclusivity. Why? Because the first result, we have done 355 sols, so 55 days Martian day on Mars, and of course we received record. I cannot show you all the results because some results are protected, of course, for research reason, but I can show you some first results, very interesting, who answer some question that I give you during the presentation. First, you can see that the solar panels are dusty now after 300 days. So that means that the energy is a key point in this mission, because when the solar panel will be very more dusty, maybe we will not have energy enough to get data. So it's important, and the data is something like that. So I can show you some data, is real data that arriving directly from Mars. So here you can see 5 days of temperature, outside temperature. So you can see the temperature at the beginning of the day increase, and then direct and slow down, of course, and begin again and again and again. And if you look at the periodicity, you can see that the periodicity is something like 89,000 seconds. That means 24 hours and 40 minutes. That means that the Martian day is a little bit longer than a day on the Earth. You can see that the shield is this protector instrument that we put on the seismometer to protect the seismometer against the wind and against the variation of the temperature. And you can see that the temperature under the shield doesn't increase a lot, and the shield is very efficient. So we don't want that variation of temperature modify a lot the behavior of the seismometer. And this is the seismometer. You can see that the seismometer is directly impacted by environment parameters, but not a lot because of the shield. So the shield, it is an instrument very, very important to get some high quality data on Mars, because Mars is a very difficult situation. There is a lot of the thermal variation are very big, and also the wind is also important. And maybe you can see this. This is 5 days also. In this blue zone, you can see the noise. It is the spectrogram of the noise. So you see the level of the noise directly recorded by the seismometer. The first 3 days were the days where the shield was not put down the seismometer, and you can see that the noise is a little bit high, so it's not very good for seismology. And then after the shield put it down, you can see that the noise reduced a lot. So that means that the shield is very important to expect that the seismograph will not be too much disturbed by the variation of the temperature by the wind. And now I would want to show you one of the first Marsquake. Yes, we have Marsquake. We have Marsquake on Mars. It was not sure, of course, because we didn't know if the energy of Mars was sufficient to have Marsquake. So it's a real Marsquake. So it's a rupture of the crust. And you can see, as you can see on the Earth, on the seismogram that you can see on the first line, you can see the P arrival time, the S arrival time. You can see on the second line a spectrogram. So this is the frequency contents of a signal, and you can see that there is energy on the P arrival, and then a new energy arrival at the S waves, and the delay between S and P waves, because these two waves start at the same time at the center of a Marsquake. So that means that S wave has a delay, and this delay is directly linked to the speed of the waves, and the speed of the waves are directly linked to the structure of a planet. So it's the beginning of investigation. If we can get Marsquake, and we can get Marsquake, you have the slide in front of you. We can have the chance to determine a little bit of a structure of an interior structure of a planet. Actually, we require not only one Marsquake, but a lot of Marsquake. Some of them are good quality, and so we can use and study with this Marsquake. Unfortunately, some of them are very little, very weak, and it's not so easy to work with all the Marsquake. But we have Marsquake. The mission is going on, and so we hope to get sufficiently Marsquake, big Marsquake, maybe very far and very close, to know better and better the interior structure of a planet. To finish this presentation, I will want to show you quickly some slides, because maybe a lot of you are teachers, and so if you are a teacher, you are maybe interested by a resource directly coming from this mission. We have action for education directly linked with the science team of a mission. So we have a contest between schools that we call Namadzu contest. If you are interested by this, you will see at the end of the presentation a website and a link to participate to this contest. The school are invited to make this friendly challenge where they have to answer to the question, to make some experiment, very simple experiment. We have also a newsletter, so everybody can receive a newsletter to know what happens during the space mission. The newsletter is something every 1 or 2 months. We have also a workshop for teachers. The last workshop was in January 2019, and the next one will be in March, the 2nd and 3rd March 2020 in Nice, with a member of the science team. So we expect 60 teachers coming from a lot of countries participate to this second workshop. We have also create some sensor like piezo sensor, pressure sensor, barometer, luxmeter, thermometer, accelerometer. So everything is in a box, in a kit, to play a lot of experiment at school and to understand maybe some complex notion with the geoscience. And finally, and maybe it's more important for you, is also to access to the data. So we have a website. On this website, you have a data center. So this data center provide all the data coming from the seismometer with a delay of 3 months. So during 3 months, the first 3 months, the researcher keep the data for themselves, and then they release the data for everybody. So what you can see on this slide is what the seismometer record 3 months ago. And every day you have new data. You have new data about the seismometer, but also new data about the pressure, usually the weather on Mars. So you can use the data, download the data, download the tools, download all you need on this website. You have also this exposition that you can use directly in the school, and you can participate to the space mission directly with your student, directly with this. And if you have on this last slide, you have the link with the website. So there is a mistake. There is a insight.oca.eu. EU is falling, and this is the mail. So if you want more explanation, more details about the expedition, you can be linked with Insight Education, and you will have more and more information about this. I think it's my last slide. Yes, it's my last slide, and maybe I can. Yes, I thank you for Eleni to put the right website address. Maybe I can answer some question. Maybe it was too quick or my English was not too clear. So please ask me your question, and if I can, it will be with pleasure to answer to you now. I think I'm on time. Yes, I think I am on time. Okay. Thank you for your congratulations.
Luc, we had
Yes.
previously from Jeremy. He asked interferometry for Mars by MRO maybe. It's in the chat.
Yes, but I'm not very aware about. I'm not very linked with this question of interferometry for Mars. So maybe I can ask this kind of question to the science team of Insight and answer to Jeremy when I will have this answer to this question about interferometry MRO satellite. Okay, so the data, it's very important to understand that this mission is one on the first mission, where the science team give opportunity to the educational community to share the data with the science team. So it's very important that the student and the teacher be aware about this. Please enjoy with this data, use the data. It was one of the priority of the science team to give the data to the community. I think if you participate to the contest, if you download the data, and if you ask questions to the science team, it's very important to show that it's important to build a link between the science and your student. And please enjoy with all this data. And I have also to thanks to the science team to give this opportunity to everybody. Thank you for congratulations. Yeah, thank you. Thank you to everybody. So maybe we will finish here, I guess. Can we say bye-bye? I look to the chat. Yeah. Bye. Bye, Almeida. Thank you, Almeida. Thank you, Jeremy, Nathalie. Thank you, everybody. Denis, bye. Ciao. Bye.